Chapter 1.10, Modeling with Functions. So this is the last section that's covered in this unit. It will be covering how to build models from verbal descriptions as well as using formulas that you may or may not recognize, but will definitely need to become familiar with. So first, what is a model, though? Many real-world problems involve constructing mathematical models that are functions. In constructing such a function, we must be able to translate a verbal description into a mathematical representation. That is a mathematical model. So example number 1. You are choosing between two texting plans. Plan A has a monthly fee of $15 with a charge of 8 cents per text. Plan B has a monthly fee of $3 with a charge of 12 cents per text. Express the monthly costs for plans A and B as functions f and g of the number of text messages in a month X. So whenever working with these types of word problems where you're going to have to be building your own equation, my first step is always to underline the important terminology, important numbers, and what they represent. So in this case, I'm going to be underlining monthly fee of $15, 8 cents per text. Monthly fee of $3, 12 cents per text. And we want to think about what those numbers really mean for us, how that's going to lead to us building our model. So, a monthly fee of $15, just to look at plan A first, means that we have this singular flat fee, is what we usually call it. So it is a fixed fee. It is one amount that we are paying, and then for every text I send, I get charged 8 cents. So that $15 does not change, but that 8 cents changes depending on how many texts I send. Or I should say, the amount of money I pay for my texts changes based on the number of texts I send. So if I send one text, I've got the $15 plus 8 cents. If I send a second text, now it's $15 plus 8 cents plus another 8 cents, then another 8 cents, then another 8 cents. And so we are changing by this constant amount. For every text I send, I am gaining 8 cents. So that constant amount or constant rate of change implies that this model should be linear, because linear means constant rate of change. That's basically what having a line gives us, is it gives us a constant slope, a slope that doesn't change. So the same can be said for plan B because it works the same way. If I'm going to build my models, I'm going to take that information where the 8 cents and the 12 cents are my slope, because that is how the amount of money I owe changes. Whereas the monthly fees are flat fees that don't change, and if I send 0 texts, that's how much I am charged. So altogether, for plan A, we get f of x equals 0.08x, so that's 8 cents times the number of text messages per month, plus the $15 flat fee. And plan B, g of x equals 12 cents times x plus the $3 flat fee. And so, to analyze what this means, what this model means, would be to say, well, the slope of 0.08 is the price per message, and the y-intercept of 15 is the price without sending any messages. Similarly, for plan B, slope of 12, or 0.12, is price per message, and 3, the y-intercept, is the price without sending any messages. Now that we have our models, we can ask questions about them. For example, which plan should you choose? Which is the better plan? Well, that's really going to depend on how you're going to use it. So, if I send 0 text messages, plan A charges me $15, but plan B charges me $3. So at first, plan B seems to be the better deal. I start off a lot cheaper. And for a while, that's true. But at a certain point, because these two lines are not parallel, because remember, parallel means having the same slope, they will eventually cross. So plan B may start out cheaper, but eventually it's going to overtake plan A because we're getting charged more cents per text. So our goal is to figure out, when does plan B cross over plan A? When does plan A become cheaper? And that's going to answer this question for us. So that point when they cross is called the break-even point. the intersection between the two lines if we were to graph it. To find the break-even, we just have to set the two equations equal to each other. So 0.08x plus 15 equals 0.12x plus 3. In order to solve this, it's just going to be some algebra manipulation. So I'm going to subtract 0.08x from both sides to get 15 equals 0.04x plus 3, and then we subtract 3 from both sides to get 12 equals 0.04x, and then I divide by 0.04 on both sides, and once I do that, 12 divided by 4 is 3, so it's going to be 300. So x equals 300. So in other words, if I send 300 texts, then basically both plans are worth the same amount. I am charged the same amount regardless of which plan I use if I send exactly 300 texts. But probably I'm not going to always send 300 texts. So the answer to this question is not going to be, oh, I like plan A better or I like plan B better. It's going to be based off of what my average number of text messages is or what I plan to do in the future. So if you send less than 300 messages in general, then you should choose plan B. Otherwise, choose plan A. That's a proper answer to this question. There isn't one right answer. It's all based off of what the person asking feels that they would do, depending on how many texts they would send. So when you have a question like this, I've had people answer saying, well, plan A has less cents per text, so I pick that one, without showing any mathematical work to say, well, yes, it's less cents per text, but if you don't send very many, it's a lot more expensive. So there's really no one right answer, so you have to make sure you're being thorough with your response. So next, example number 2, on a certain route, an airline carries 8,000 passengers per month, each paying $100. A market survey indicates that for each $1 increase in ticket price, the airline will lose 100 passengers. Okay, so let's go through and do our underlining step. 8,000 passengers per month, and they pay $100, so by default, they pay $100. But for a $1 increase, they will lose 100 passengers. If we want to express the number of passengers per month, we'll call that n, as a function of the ticket price x, that means we're going to write some function n of x. And we need to relate all of this information to say how many passengers we're going to have based on how much we increase or decrease the ticket price. So we know that if the ticket price is $100, we get 8,000 passengers. So we have this point, 100, 8,000. And then I can come up with another point. For example, if I charge $101, then I will have lost 100 passengers. So in other words, we get 101 and 7,900. $101, 7,900 passengers. Okay, so these are 2 points. Having these 2 points can guide us to make sure that whatever formula we write down, we'll know it's correct if both of these points work for that formula. Because a problem like this can be fairly tricky. You might first think, oh, okay, 8,000 is that fixed rate we have, that fixed number. So it'll be 8,000, and then we just need to figure out what our slope is. And there's a lot of hundreds in here, so maybe our slope is 100. But we're losing 100, so maybe our slope is negative 100, which in fact is true. But there's a little bit more going on here. So you really need to make sure that these 2 points actually fit into whatever equation you come up with. So the equation I came up with is n of x equals 8,000 minus 100 times x minus 100. So notice that if my equation had been simply 8,000 minus 100x, then that point, 100, 8,000, would not fit into this equation. If I plug in 100, I get 8,000 minus 100 times 100, which would be 8,000 minus 10,000, which is negative 2,000. So if we charge $100, then we have negative 2,000 passengers, and we know that's not true, so this can't be the equation. Instead, we have to sort of shift where the beginning of our pricing is, because we have this default price. We know that paying $100, we know that if we pay $100, then we get those 8,000 passengers. So if we start from 100 and work our way down, then we can come up with a better equation that actually will fit this point. So if I plug 100 in here, 100 minus 100 is 0, so I haven't lost any passengers. But as soon as I plug in 101 into here, now that's 101 minus 100 would be 1 times negative 100, so that's minus 100. So total would end up being the 7,900 if I'm plugging in 101, which we knew was one of the points from back here. So yes, both of my points work in this version of the equation. So sometimes you're going to have to shift it around. If you are confused about the structure of this particular linear function, I encourage you to look back at the different types of linear equations that we can build. Again, this is not something that is covered super thoroughly in this class, but this is based off of using the point-slope form of a linear equation instead of using the slope-intercept form. They're both, if those words mean nothing to you, definitely look back to chapter 1.4 and 1.5 and see the different types of linear equations that we can run into. They all map the same thing, but they're different ways of representing it, and so this is based off of the point-slope form, where all we need is the slope and a single point to build the equation. So anyway, I have this equation now. I have this equation that models the situation, and it models it accurately because I can plug in a couple points. I can plug in any point that I could come up with, and it would end up being true. So now I'm just going to simplify it so that it looks a little bit nicer. Once I do that, I'm just multiplying in that 100 and combining like terms. I get 18,000 minus 100x. So the next question is, express the monthly revenue R as a function of that same ticket price x. So revenue is all about how much money I'm taking in. So how much money am I taking in is going to be based off of that ticket price, but it's also going to be based off of the number of passengers. So every passenger pays that ticket price, right? So we have a variable, we'll call it for a moment, that represents the number of passengers, but really that variable is a whole function. The number of passengers is n of x. So really, to find the revenue, it's the number of passengers, n of x, times x. Don't get confused here and write n of x squared. Remember that function notation doesn't work that way. N of x is all one quantity of a thing. You can't break that apart and bring that x in to make it x squared or anything like that. It does not work that way. So n of x times x. And then we know n of x is written right here. So we're just going to replace n of x with that formula we found in part A. So that'll be 18,000 minus 100x, all multiplied by x, which I have distributed that x in and then rearranged it just in a more standard order. You don't really need to do that, but our final answer is negative 100x squared plus 18,000x. So this means that that I could calculate the amount of money that I take in based on whatever the ticket price is. And then later on in this class, we could take this equation and we would know how to figure out what the best ticket price to sell tickets at would be. That is, we could figure out where the maximum value of this formula is. So that's one of the goals of Chapter 2, is finding maximums of a function like this, because then we could say, how much money could I possibly make? How much should I sell these tickets at to make the best profit? That is our goal when calculating a revenue function. All right. Now, the last topic for, well, really this whole unit is modeling with geometric formulas. So you'll see on the right here, I have a whole bunch of common formulas that you should know. And if you don't know them right now, that's okay, but you should re-familiarize yourself with them, because a lot of them will come up. There are some that you definitely need to have memorized, others that you probably don't need to necessarily memorize for this class, but you can't be certain, so it's good to just have an idea about all of them if you can. Yes, the volume of a sphere or the volume of a cone probably not going to come up in Pre-Calculus 1 on a test, but if you're heading on to calculus, it very easily can. So now is a good time to start trying to memorize them. But for right now, really what you need to know is how to find the volume of a box, how to find the area and perimeter of a rectangle, circle, cylinder. Those are the base ones that you'll see the most often. So for this problem, we have a machine produces open boxes using rectangular sheets of metal measuring 15 inches by 8 inches. The machine cuts equal-sized squares from each corner. Then it shapes the metal into an open box by turning up the sides. We want to express the volume of the box V in cubic inches as a function of the length of the side of the square that was cut from each corner, which we'll call that length X, in inches. Then we will find the domain of that volume. So here, you can see that luckily we were provided a drawing. So we are cutting out this little square X from our box, or from our rectangle, which allows us to sort of fold up the sides. So if you're having trouble picturing it, how this becomes a box, think about this side would then be folded upward, same for here, folded in, folded up, folded like that, and so we get these four sides, this box. The box does not have a lid. So our goal is to figure out what equation do we need to use and then fill out that equation. So this, once it becomes a box, it is a rectangular solid or a rectangular prism. So we have the equation for that right here. V equals LWH, or in other words, length times width times height. And so we need to figure out what is our length, what is our width, and what is our height. So if we look at this box the way it is, it might not be totally obvious what those are, but think about what it would look like when it is constructed. So 15 and 8 look like they might be the length and the width, but in fact that's a little tricky there because we've cut away those x's from it. So in fact, this is our length, this 15, and then we've cut away 2 x's, so minus 2x. This is our width, which is the 8 with the 2 x's cut away, so 8 minus 2x. But what is our height? Well, our height is, when we fold it up, it's going to be those x's. This gives me the height, x. So altogether, we get the following. And here we can even draw a constructed picture of that box. So 8 minus 2x, 15 minus 2x, and x are our length, width, and height. So now we have an equation for our volume. And yes, we could multiply this out if we wanted to, but really leaving it in this factored form gives us slightly more information than multiplying it out would. So I'm going to leave it this way, and that's a fine answer. So now let's look at finding the domain. So remember that when we talked about domain in the past dealing with equations, I said really the only thing you had to look for was denominators can't be 0, we can't have negatives under even roots, and there might be restrictions just from it being a piecewise function or just given restrictions, etc. But none of that is really happening here. This isn't a piecewise function. There's no denominators. There's no even roots. So this function as it's given, 15 minus 2x times 8 minus 2x times x, should have a domain of all real numbers. And as an equation, it would. But when we put it in this context, when we put it into a real-world situation, that's where we end up with further domain restriction based on, well, reality. So, in fact, no length can be negative. In other words, I can't cut away such a large x that one of my sides is negative 2 inches. That wouldn't make any sense. So we have to make sure that all three, the length, the width, and the height, are positive. And in fact, you have two options here. We could say they are positive or zero. That's called having a vacuous box, and you can do that, and there are reasons to do that, which you will address further in calculus, but we're just going to say it has to be, all of these lengths have to be greater than zero, just because it makes more sense in real world situations to say, yeah, we have to have them larger than zero, because if a length was zero, we really wouldn't have a box at all. So we will take each of these lengths, the length, the width, and the height, and state that they have to be greater than zero, like so. Then, to figure out the domain, we're just going to simplify each of these equations so that it tells us, in the end, exactly what our restrictions on x have to be. So to do that, we're just going to solve the inequalities. So first, we're going to subtract 15. So we get this negative 2x is greater than negative 15. Then we divide by negative 2. And so here's something, once again, we've seen this before. You have to remember that when you divide or multiply by a negative number, only if it's negative and only if it's division or multiplication, the direction of our inequality is going to switch. So we get x is less than 7 and a half, or 7.5. And we will do the same thing for the next one, so that we get negative 2x is greater than negative 8. We do that division, the inequality switches directions, so we end up with x is less than 4, but x is greater than 0 just stays the way it is. There's nothing we can do there. So to finish out our domain, we want to look at the intersection of all three of these statements. So if I was to draw a number line right here and place all of these numbers on it, 0, 4, and 7.5, I know that I have to be less than 7.5, I have to be greater than 0, and I have to be less than 4. So the area where we have drawn the arrow all three times, this is the intersection of all these three intervals, that's the actual domain of our function, from 0 to 4. And notice that, once again, this is not inclusive of 0 or 4. So our domain, 0 to 4, we're using parentheses as we are not including 0 or 4. All right, so our final example for this unit is you have 200 feet of fencing to enclose a rectangular garden. Express the area of the garden, A, as a function of one of its dimensions, x. So this is going to be probably the most common type of problem from this section. So make sure you understand how to do this, because I can pretty much guarantee it will come up on a lab or a test or something later. So you need to know how to do this. So first, we're going to figure out which equations we need. This is a rectangular garden, so we're going to need the equations that have to do with a rectangle. That is, we have a perimeter and an area. So which equation do we need from that? Well, in fact, we're actually going to need both. So the information we are given at the beginning is that you have 200 feet of fencing. So in other words, all going around here, the fence has to be 200 feet. Well, all around that fence, that is the perimeter of our garden. So our perimeter, our 2L plus 2W, I'm going to convert that into 2x plus 2y, simply because that is what is given in the drawing and told to us in the description of the problem, but it's the same thing. So our length is x, our width is y. It's all equal to 200. Our perimeter is 200. Now our area is length times width, though, and we just said, well, that's the same thing as saying x times y. But that doesn't really help us find the area of the garden as a function of one of its dimensions, x. Like, my goal is to get that area, but only have x in there. So how do I do that? I'm going to have to get rid of y. And in order to do that, I can use the perimeter equation. So I'm going to take 2x plus 2y equal to 200, and solve that equation for y, so that I have a function of for y with respect to x. When I do that, I get y equals 100 minus x. So that's just, again, 2y equals 200 minus 2x, and then I divide everything by 2. So once I divide everything by 2, I get y equals 100 minus x. So that allows me to replace the xy. So this x times y, the y is going to be replaced with 100 minus x to get x times 100 minus x. That gives me an equation for the area. Yes, again, I could multiply this out further to get 100x minus x squared, etc., just if I wanted to, but for right now, this is fine, and it gives me a little bit more information to help me figure out a domain if I wish to. So what would the domain be here? We're still in a situation where I have to say we cannot have negative length. So we will be restricting our domain from x greater than 0 and 100 minus x greater than 0. So x greater than 0 already tells us something. I don't need to do any manipulation there, but here I'm going to solve. Remember, we switch the direction when I divide or multiply by that negative. So x is less than 100, x is greater than 0. So drawing out the number line gives us, here's 100, here's 0, we're less than 100, we're greater than 0, so we are this area in the middle. So our domain in the end is from 0 to 100. And so that is it for this section, for this whole chapter, which is this whole unit. So hopefully you've followed along pretty well. Make sure to try out the practice questions here, particularly the second one, because like I said, that's a type of problem that does come up very often. So make sure you're understanding how to work with those rectangle and rectangular perimeter versus area problems.